really wish to talk about today is pretty much straightforward and simple. What I will just show how the simplex algorithm in one dimension can be looked upon as a very particular case of random walk, rather, I must say, a Markov chain. Uh, so, I will, don't worry, I will discuss the definitions of random walk, Markov chain, and whatever I have said. So, I think we're good to go. So, let's start. Okay, what I aim to deliver today. It's a very brief overview what I have prepared today. Firstly, the basics of one-dimensional random walks in discrete state and discrete time. Then I will discuss a few properties of random walk, and I think those properties are really simple and interesting. Then, moving a bit from probability, I will discuss about what do you mean by simplex algorithm, and I will discuss a few fundamental definitions of optimization theory. Then I will geometrically interpret the simplex algorithm, which is interesting, I believe. Then directly into the topic, uh, which is the fourth thing I wish to discuss, is how simplex algorithm can be seen as a random walk, in general, a finite Markov chain. And lastly, if time permits, I would like to discuss a few problems. Okay. Okay. So, what is a random walk? What is a random walk? The term random walk is pretty much self-explanatory, I believe. I will just give an example before going to the formal definition. Suppose a man is standing at the origin of the Cartesian plane. Cartesian plane is a two-dimensional plane, and he is allowed to move exactly one unit to his left or to his right in the very next steps. And very importantly, I must mention here that he is not allowed to move any other directions like upwards, downwards, or diagonally. He is allowed to move only left or right. Also, he is not allowed to stand still in any time point, but he has to move either to his left or to his right, with some probabilities, not necessarily with equal probabilities. Well, like this, after certain time points, say after n time points, n is a finite number, the man would end up somewhere in the x-axis, which is trivial. Like the man is moving left and right, so the man would end up somewhere in the x-axis itself. In fact, it's pretty much possible that the person might end up in the origin again. Yeah, if he takes equal number of steps towards right and towards left, then the person will end up in the origin after even number of steps, definitely. Okay, so let's look into the definition. Random walk is nothing but an IID series of random vectors. The random vector is a generalized term. We are only focused in one dimension, so the random vectors are simply random scalar variable. Well, here I have highlighted the word series because it's not a sequence, but it's a series. And the term IID stands for identically and independently distributed series of random variables. In one dimension, as I have illustrated in the example also, the random variables can only take two values, not necessarily with equal probabilities. So let's jump into the formal definition. Suppose we have a IID sequence of random variables such that the probability distribution of the random variables are given by a random variable can take only two values, +1 and -1, with probabilities p and 1 minus p respectively, where p is definitely a real number strictly lying in between 0 and 1. Then in a particular time point n, okay, before coming to this, I would like to say something. Well, in the example of the man starting at the origin, if you remember, I have talked about the origin. Well, the man was starting at the origin, but generally, it's not really required to start at the origin. If you notice, the man can start anywhere in the x-axis. Okay, and call that random point as A. Random I mean the arbitrary point A. So that's why here I have defined the starting point of the man as A. A is not necessarily the origin. A can be any point of the x-axis. Okay, so in a particular time point n, Sn is nothing but the sum of the starting point and the preceding n many random variables. So intuitively, if you see the random variables xn's take values +1 and -1. So Sn is vaguely the position of the random walk at the time point n, and that's the random. Then, and that's the concept of random walk. Then the series Sn is called a random walk on the positive integers. So random walk is a sum of IID sequence of random variables. At the time point n, it's a sum of n many variables, and the random walk can go on forever. So I'm not giving any bound of the sequence. That's why. And clearly, the difference of any two preceding value of S is strictly 1, because the man was allowed to move exactly 1 unit towards his left or towards his right. Okay, there's another thing. When the probability of moving to left and right is equal, that is, the P is equal to half and Q is definitely equal to half, then the random walk is called simple systematic random walk. It's just a definition. Okay. Okay, now in this context, I would like to discuss uh, two results of one-dimensional random walk, and I believe these are fundamental theorem of whenever a person starts to study random walk. Okay, the first one is reflection principle. The reflection principle is very easy and fundamental, yet useful principle. uh, it says, I will just read out from the slide. The number of all possible paths from a point A is a point here, to another point B in n many steps, which hits the x-axis on kth time point. Kth time point is k is a integer lying between 0 and n. So the random walk is moving from A to B in n step, and in the intermediate step, the random walk hits the x-axis, that is in kth time point. And this number of all possible paths is equal to the number of all possible paths from -A to B in n many steps. The proof of this theorem is easy, but I'm not planning to discuss it today. But I can give a brief overview of the proof. The proof goes as like, suppose the theorem says that there exists a point K at which the random walk hits the x-axis. So from A to K, from 0 to K, in the time point 0 to K, the walk is moving from A to some point. In the kth time point, suppose A to 0, so the random walk is hitting the x-axis. So in the time from 0 to K, the random walk is moving from A to 0. So the walk is reflected along the y-axis from -1 to 0, and that's the idea. And I'm not really planning to discuss the proof. Rather, I would discuss another theorem where this principle is used. Okay. The second result I would like to discuss is Ballot theorem. I will just read out the statement from the slide, and then I will explain why the name is Ballot theorem, why the term ballot is there. Okay. suppose b greater than 0, b is the point where the random walk is uh, where the random walk reaches after n many steps. The number of paths from 0 to b in n steps which do not hit the x-axis is equals b upon n times number of all possible paths from 0 to b in n steps. So it's nothing but a fraction of the all possible paths from 0 to b in n steps. I will formally define the theorem. Okay. The ballot problem, I have taken this statement from Wikipedia. Well, this problem, I will just discuss. Okay, it's quite visible from the statement of this problem, where this problem actually from where the problem actually came from. Suppose in an election where candidate A receives P votes and candidate B receives Q votes with P greater than Q. So clearly A is winning. The probability that A will strictly ahead of B throughout the counting is P minus Q by P plus Q. That's the actually ballot theorem. Okay, I will just connect with the previous counting theorem. I just mentioned that with Ballard's counting theorem, and I just what say this. I just said this as a Ballard theorem of counting to differentiate from this theorem. So, for, as per the usual notation from the previous theorem, I get that b equal to p plus q and n equal to p. Sorry, b equal to p minus q and n equal to p plus q. Why? Uh, as per the usual notation, b is the point where the random walk reaches after n many steps, after moving left and right and so on. Since here you have to define something like the vote of the define that the vote of the candidate A with right step and the vote of the candidate with left step. Okay, so I am associate okay, let me summarize. I am associating P with the number of steps towards right and Q with the number of steps towards left. So that's the difference. The B is the point where the random walk was reaching in this time point n. So there's a difference, and that's why B equal to P minus Q. And since P is greater than Q, so B is the difference. And n is P plus Q, which is quite trivial because in a time point n, we are only considering P. We have already counted P plus Q votes. Okay. Moving a bit from Markov chain, in this context, I should have discussed my Markov chain first before I discussed random walks. Before random walks are nothing but a very specific case of Markov chain. But I think the concept of Markov chain is a bit twisted, and the random walk is really obviously one-dimensional random walk is easier to visualize easier to visualize. Okay, so Markov chain is a chain that forgets its past. I have written that sarcastically. Okay, formally speaking, for a given time point, the conditional probability of moving to a state given the chain depends only on the immediate last visit. Here, I would like to say that a state space. I have used this term in many places in this slide. What is a state space? State space is nothing but a set of points where the chain in the previous section, the chain was the random walk. Here I am talking about generalized chain. Suppose here the man is allowed to move anywhere in the x-axis. Okay, not exactly left and right, not exactly one unit. He can move any unit towards any of the directions of the x-axis. So in a generalized chain, the state space is the set of points where the chain takes values or the random variables takes values. and time is also a set, that which time is also a set where the points are the time points. Okay. Okay, for coming back to this, for a given time point, the conditional probability of moving to a state given the chain depends only on the immediate last visit. Okay, I would show the actual definition. Okay, formally, we are only focused in discrete state space and discrete time. That means the state space, the set I have just mentioned, is a countable or a finite set, and the discrete time means the time, the set associated with the time is also countable. Okay, a Markov chain is a stochastic process. Okay, the stochastic process is nothing but a sequence of random variables. Definitely, IIT sequence of random variables that takes values in a countable set in the state space. Okay, a Markov chain is a stochastic process taking values in a countable set, the state space. If for any n greater than 0, n is a natural number, and we have some elements of the state space, that is I naught, I1, I2, up to in minus 1, and then I and j, we have probability of of the chain hitting the state j, given that the, the chain has visited the chain has visited the states in I naught in 0th time, I1 in first time point, I2 in the second time point, and I n minus 1 in the n minus 1th time point, and finally in the nth time point the chain has visited the state I, and which is equals to the probability of the chain hitting the state j in the n plus 1th time point, given the chain has visited the state I in the nth state. So the informations regarding the state, the time point 0 1 2 up to n minus 1 is becomes redundant. Okay, so you can get the feel that the Markov chain is a chain that forgets, it only remembers its immediate past. Okay. Fine. Okay, when the set S, the state space I have mentioned, is finite as well, then the Markov chain is called a finite Markov chain on S. This is the definition uh, I would be using further. Okay, too much probabilities. Okay. Okay, moving a bit from probability. Later on, I will again come back to Markov chains. For the time being, let me discuss a few few basic definitions of optimization theory. The first and foremost definition, that is LPP. LPP stands for linear programming problem, and we all have heard this, and we all have studied this. This is in our plus two, and so I will just quickly recap this part. Linear programming is a technique. Definitely, LP is a technique to optimize a linear function subject to a system of linear constraints. The optimization stand for maximization and minimization for the time being. Then the next important term is the objective function. Objective function is nothing but the function that I want to optimize, to minimize or maximize. It's called the optimize. It's called the objective function. Okay, now I will just define LPP formally. Okay, suppose there are p linear constraints involving n variables. Definitely, p is strictly less than n. So, LPP, a linear programming problem, can be formulated as, we have to just search a n component vector that maximizes a linear function, that is the C transpose X, subject to a system of linear constraints. Rather, I must say that a system of linear inequalities. A is a matrix, B is a vector, C is a vector, and definitely uh, X is also an component vector. And also the constraints, firstly the constraint, that is a x curl less than equal to b curl, it's a system of linear inequalities. Along with the, this is a very necessary and sufficient condition, that is the x curl must be greater than equal to 0 for the problem to be solvable. Okay. Okay, the simplex algorithm is used in convex optimization. Simplex algorithm is nothing but a bit extension of the LP. Yeah, sure. Okay, I was planning to say this after this, right after this slide. Thanks for thanks for pointing me out. Just wait a few more lines, then definitely, yeah, yeah. Okay, the simplex algorithm is mostly used in convex optimization. Suppose a LPP is given in a canonical form. The form I was written in the previous slide is known as the canonical form. Okay, to maximize without loss of generality, I am considering the problem is a maximization problem. I have to maximize a function, a linear function, subject to the constraints, subject to the system of constraint a x curl less than b curl, and obviously x curl 0. Okay, where c is the coefficient vector, x are the variables, a is the coefficient matrix, and so on. Okay, now the important part, the feasible region. What do you mean by the feasible region? The feasible region is nothing but the set of x curl. I am talking about the n-dimensional real space. The feasible region is a set of x curl satisfying this particular condition, that ax curl less than b curl and x curl greater than 0. If you think about it geometrically, the feasible region is a region in the n-dimensional space where all the what's it possible values of x curl satisfying these two conditions lies. And we are lucky, we are, I say that, I must say that we are lucky enough, the feasible region of this problem is a convex set having exterior points. Okay, I will discuss this uh, later on. Before that, the I would like to say a few things about the question Moitro has raised. Yeah, it's a very nice observation that all along we are only talking about convex optimization, because the optimization in convex set is easier and straightforward. Firstly, in convex sets, we can assure that the optimization can be performed. That is very important. That means at least one of the solution exists. We don't know whether it's a good solution or bad solution, but a solution exists in case of convex optimization. And for convex optimization, there are conventional techniques and methods and formulas to find solutions. But whenever we move from the convex scenario, when the problem is not convex, we cannot guarantee that the optimal solution of the problem exists. That's the first point. Suppose the solution exists. For the time being, consider the solution exists, but there is no conventional method of finding that. I mean, the techniques of finding such solution, if the solution exists, solely depend on the problem statement. I mean, we don't have like this conventional algorithms and so on. So we are just focusing on the complex optimization to make our life easier. Okay, yeah, I hope I could answer that. Exactly, exactly. Okay, we are lucky enough here. We are extremely lucky that the feasible region of the problem the is convex, and also important, the convex set having exterior points. Okay, it's a property of the convex optimization that we can assure there's a rigorous proof, and I'm not really planning to discuss it either. It can be shown that the maximum of the objective function, since we are discussing the maximization problem or the solution of the LPP, if it exists, definitely can be achieved only on one of the exterior points. That means I have said that we had to search n-dimensional vector that optimizes the objective function. So now our search is easier. We just have to check the exterior points of the convex set, the feasible region. So the search is what's limited here. The number of exterior points can be finite or infinite. Definitely, by infinite number of exterior points, I am referring edges. Also, it can be shown that if the number of exterior points is infinite, the feasible region becomes unbounded, and hence no solution exists in that case. Okay, these are some important results regarding the optimization. Now I will okay, so the focus now we have just to we have to maximize or minimize the objective function subject to or being constrained in a convex set having finite number of exterior points. That means we have to just check finite number of points, and among those points the optimum solution will lie. So the search seemed really impossible in the beginning, but the search is not that tedious so far. Okay, now I will talk about the geometric interpretation. uh, I have given an essence of that already. I have mentioned how the feasible region, how the feasible set can be visualized as a region, as a closed and convex region in the n-dimensional space. So so the thing might be easier to visualize geometrically. The feasible set is nothing but a polytope. That means a n-dimensional region having n vertices, having finite number of vertices, not n vertices, finite number of vertices and edges in n-dimensional real space. Polytope is nothing but the higher dimensional generalization of polygon. So the green thing is a polytope. It's a how the feasible region of a problem can look like. This image I have taken from Wikipedia. For the time being, I'm skipping what the red line is denoting here. I will definitely come back. Okay. Now the simplex. Why the simplex algorithm is so special? Why there's an algorithm called simplex? The simplex algorithm is an algorithm that assures that the solution of the optimization problem, rather the convex optimization problem of a linear programming, lies in one of the vertices. That I have also in the previous slide I have also mentioned that the convex the search is now constrained into in the finite number of exterior points. The exterior points are the vertices here. Okay. Further, the job is now to move from one vertex to another to get the optimum choice of x. And since there are finite number of vertices, so the job is not that tough. Okay, the search is this all I have said before. The search is not arbitrary as it seems. Intuitively, one should move in the direction of the objective function in a maximization problem. Okay. The speciality of the simplex algorithm, why the simplex algorithm is so vital, is the simplex algorithm just ensures that while moving from one vertex to another, the algorithm ensures that I don't move to a worse vertex. I mean, for a maximization problem, the simplex algorithm the simplex algorithm guarantees that I don't move to a point where the value of the objective function decreases in a maximization problem. That's why the term wars, the wars vertex, is okay. So I think I have discussed all the preliminary definitions and results I needed to discuss. So I will quickly jump into the what my real objective today. What my real objective is. Uh, I will. I have discussed two different concepts. First, for the in the first section, I discussed probabilities, random walks, Markov chain, and so on. In the second section, I have discussed how the optimization works, how the convex optimization works. So I would just try to mix those topics. I would just try to mix those topics. Okay. So I will mixing up probability with the simplex thing I have just said. Okay, so as for the optimization, vaguely, if I say vaguely, it's all about moving from one vertex to another in each step. So can you connect it with a random walk as I said, because the person was moving from one point to another in a particular time point, and this is all, and the simplex algorithm is all about that. But there are certain problems, like I cannot go to any of the vertex, rather I have to move to a better vertex. It's not really random walk, rather a generalized Markov chain, a finite state space Markov chain. The process of optimization can be viewed like this. The process is a discrete the optimization process, the simplex process I have just mentioned, is a discrete state Markov chain having an arbitrary starting point. In When you are doing the optimization, you start from any of the vertex of your choice. That's why an arbitrary starting point I naught, the chain moves to all the available and better vertices, because the simplex algorithm ensures that I never move to a worse vertex with this with equal probabilities. This part is important. I can move to any of the available and better vertices with equal probabilities. The chain is indeed finite. Why? Because the optimizer I have said before, I would just like to make you remember that the optimization problem admits a solution if there are finite number of vertices. So the state space of the chain, the Markov chain, are those vertices. So suppose, since we're dealing with finite number of vertices, the Markov chain is finite since it has finite state space. Okay. Okay. So I think I would like to discuss this interesting problem. Uh, okay. So the problem. Yeah. Suppose there are n choose m vertices in a simplex polytope. M is strictly less than n, such that a convex set with n choose m vertices ranked in order of merit. What I mean by order of merit is, I think it's clear to you, with no matches. There's no tie. I'm considering no tie case. Like there does not exist two vertex. There does not exist two vertices where the uh, objective function takes the same value. Okay. So there are n choose m vertices ranked in order of merit with no matches. One seeks to reach B, the best vertex, that is our the object, that is the optimal solution from jth based vertex. Jth based vertex is the arbitrary starting point from where you have started. So one can go any of the j minus 1 better vertices with equal probabilities. Now, what is the expected number of steps to reach B from the jth based vertex? So this I'd like to I'd like to say a few words about significance of this problem. This problem is nothing but a bookish problem, but I think this problem is very interesting because in while performing simplex algorithm, one starts from an arbitrary vertex, and then the and then you move to another vertices in the next iterations. It's a very natural question that after from if I start from a point or a vertex, how many iterations will take to get the optimal solution. So in my UG days, it was these questions really bothered me. So this problem is nothing but a bookish problem, but I think for this reason, this problem is significant and I really found it interesting. Okay, I would just I would just illustrate an approach to the problem. Okay, I won't discuss the solution in details because it's nothing but mathematics. I just wanted to give the essence of the problem. That was my main motive. Okay, so I will just discuss the problem quickly. Fix a j, fix a j, and then with corresponding to the j, define an indicator random variable. Indicator random variable, you all know, is a random variable that takes a particular value with probability 1 and which takes only a value with probability 1 and it takes no other values. So I am defining a random variable which takes the value 1 and 0. Okay, I would just say it like that. Okay, the ith indicator. Okay, please read it out. Exactly. I have taken that problem from there only. Yes. Okay, so I am defining the ith indicator variable as the variable takes 1 whenever the xi is the random variable after the jth iteration equal to n minus j minus 1. N is where the n choose n, uh, and the indicator variable takes 0 otherwise. So the indicator uh, it's really easier to write the problem as indicator because we know the expectation of the indicator is the probability. So I will just have to, if you notice, we have to just find the expectation of this indicator variable, and that's nothing but the probability of this event, that is x I equal to n minus a minus 1. And since the simplex algorithm, and the problem statement says that the walk is moving to any of the n minus j minus 1 vertices with j minus 1 vertices with equal probability, so the probability will be 1 upon j minus 1 for all I. The probability is depending nowhere in I, so I will just get that probability of Sorry, I have written it wrong. This will be the expectation of EI is equal to 1 upon J minus I. Okay, now I am defining the Sj, another random variables, that is the number of steps to reach the best vertex starting from the jth base for a particular path. The expected number of visits, the expected number of steps to reach B from jth vertex is expectation of this random variable Sj, and Sj, if you notice, Sj is nothing but the sum of the indicator variables I have denoted by uh, capital upon capital I with index small I, and the sum would run from 1 to j minus 1 because we have j minus 1 available vertices, and among those j minus 1 vertices, the exactly one vertex is the best vertex, that is B. So this is a simple algebra, and I have reached that the expected value of the expected number of steps to reach B from the jth vertex is the sum running from 1 to j minus 1, P running from 1 to j minus 1, 1 upon P. So easily one can calculate the expected number of iteration till the problem is the one can reach the optimal solution. Okay, I think, okay, there are some prospective problems I think can be contextual. Okay, suppose in context of the previous problem, suppose one starts at the worst vertex. Okay, so there are no ties if you remember, and there are n choose m vertices. Suppose one starts from the worst vertex. You know what I mean by worst here, and moves towards the best. For a large number of vertex, suppose the number n choose m is very large, we have to derive the asymptotic expression of the expectation. Well, I am not planning to discuss this how the expression is derived, but I can give a hint that if you write down the expression like this, you can use the Starling approximation to reach asymptotic expression, and the expression is a closed form. It's not about it's not in the form of some infinite sum or something. It's a closed form. Okay. The second question is really trivial. What is the expected return time of a particular vertex? I guess it's a very trivial question. It's a because I would just explain. Suppose you have start you have started in a vertex and you are moving towards the best. The simplex algorithm assures that you never hit worst vertex. So after starting from a vertex, you will never return to that vertex because you will only move to better vertices onwards. So the expected return time of a particular vertex is trivially 0. You will never visit a vertex twice. And that's the beauty of simplex algorithm, and simplex algorithm assures you that. Okay, so I think I have discussed what I had in my mind. So I will just quickly summarize the whole thing. It will hardly take two or three more minutes. Firstly, I have discussed the random walks, then Markov chains, and then I have discussed simplex algorithm, how simplex algorithm is useful in the context of optimization. Then I have shown how the simplex algorithm can be seen as a Markov chain, a finite state Markov chain. Now I can use the term Markov chain, finite state space Markov chain. And yes, I think that's it for today. So here are the reference. from where I have taken the problems and the definitions. And thank you for being with me. Yeah, sure. I think I'm stop. I think I should stop presenting. If anyone raises a question from any particular part of my slide, I will just present that part. Okay, sure. Sure thing. Mm, okay, hold on. This one. Okay. In the previous slide, this is not a probability. Okay, you can see my cursor. This is not a probability. It's a very bad typo, I must say. It's the expectation of the II. Okay. Yeah, yeah, yeah. Okay, yeah, yeah. This is a very bad typo, I must say. Sorry for this mistake. Okay. Okay. Uh, yeah, but yeah, the traveling postman problem is itself a stochastic problem. I mean, as far as I know, the problem is itself a probabilistic problem. It's a more general Markov chain where the okay. Here I have considered that the Markov chain, if you remember the expression of the Markov chain, the probability is was only depending on the very previous step. Suppose the Markov chain, the conditional probability depends on the previous two steps or three steps and so on. Those are more generalized Markov chains. Also, there's a property called strong Markov property. Here I have specified a particular time point t. If you notice in the whole slides, I have only talked about for a particular time point t. If the time point t is not fixed, if the time is also random, there is a property called strong Markov property. That's a uh, way more generalized Markov chain and properties. So there that can be used, I guess. So the answer to your question is the traveling postman problem. Uh, is viewed as a stochastic problem only. I mean, I have never seen any other approaches to deal the problem. I might be wrong, but I have never encountered any other approaches apart from probabilistic approach. Okay. Firstly, I would like to ask what do you mean by discontinuous time processes? If you mean here I am only discussed about it's a discontinuous time processes only because I have considered the time to be discrete. If you mean that, I have discussed all the results and everything in discrete scenario only. If the time is continuous, the things become more general and complicated, and it's not quite clear to me what do you mean by discontinuous time. Can you further clarify? Yeah, please. Okay. I guess Mandas has written that he's not referring to discrete time. Hello. Okay. Okay. I now I get it. Okay. Uh, Probably there's a problem with the chronology, I must say, because the Markov chain and the stochastic approach is a more generalized thing, and the simplex is a whole other thing, and the optimization is a whole other thing. In the these topics and here in the simplex, I have illustrated simplex as a application of Markov chain, and it cannot be the way around. Like you cannot define Markov chain as simplex or something like that, because the simplex is a whole different topic. If I get your point, you are referring to discontinuous time processes. Those are more general Markov processor or stochastic processes, I must say. I really doubt that that can be viewed as an optimization problem. It's very debatable whether there can be linked with optimization problems in that context. Okay, the optimization this particular optimization problem can be viewed probabilistically, or the Uttalok has asked the traveling postman problem. There are certain problems in the optimization that can be solved or approached probabilistically, but we cannot assure that the problems that every problems in the optimization that every problems in the probability or the stochastic process can be expressed as optimization. It's a one way process, I must say. I think could I answer your question? Okay, I think that's it. Thank you guys for attending.